rate of change of polynomials and subtraction of polynomials. When we talk about the rate of change, we're really talking about the slope, the rise over the run. And as we learned in Algebra 1, rise over run can be found just 2 points. 5x1 and y1 for one coordinate, x2 and y2 for another coordinate. If I subtract the actual numbers of y2 minus y1 over x2 minus x1, I get the slope. And remember, the rise is the y coordinate, and the x is the x, and the run is the x coordinate. So that's why I talk rise, which is the y, over here, and then the x is the run, well, the walking across, actually. And I've got 2 points here. 3, 9 for point 1 and 7, 17. This with 2 points, we can find out what the slope is. And this is point 1, this is point 2. I'm going to take y point 2, which is 17, minus 9, and that's my y2 minus y1, which is 8. And I'm going to take my x2, which is 7, minus my x1, which is 3. 7 minus 3 is my x minus x1, that equals 4. So I got 8 over 4, which gives me a slope 2. And basically what I'm looking at here is my slope is 2. It's the rise over the run. For every, if I start over here, so I'm just looking at any one x point, that's right on the line. If I start right here, I go 1 up. I go 2 across, the equivalent. And I can go right here. I go, it's a 2-to-1 ratio. So if I go 1, 2, 3, 4 across, 1, 2, 3, 4, 5, 6, 7, 8. So that's a ratio. No matter where I go between the 2 points, it is a 2-to-1 ratio or a slope of 2. Now, I'm going to also have slopes of nonlinear. This is a polynomial equation right here, and this actually is x cubed minus 4x. Now, it changes all over the place. The slope is constantly changing. It's different here than it is here, than it is here. Remember, we're talking about slopes towards the end of the semester here. But a slope is basically what's tangent to that line. So if I've got 2 numbers, I can find out what is the slope between 2 points. And I got this one point here, negative 2, 0, and 3, 15. I put negative 2 in here in this equation, x cubed minus 4x. And negative 2 cubed is negative 8. Then negative 4 times negative 2 is plus 8. That equals 0. So my first point is 2, 0, negative 2, 0. My second one is I put in 3. 3 cubed is 27. Minus 4 times 3 is 12. 27 minus 12 is 15. Hence, I get 3 over 15. Now, my 2 points here, negative 2, 0, positive 3, 15. And I'm subtract my y2 minus y1 for over x2 minus x1. 15 minus 0 is my y2, my y1. 3 minus negative 2 is the same as 3 plus 2, which is 5. I got 15 over 5, which equals 3, and that is a slope of 3. Why do we want to look at rate of change with polynomials? What I have here are population pyramids. They're kind of interesting because you can use a lot of the polynomial nomenclature to determine what happens in populations. A population pyramid, let me explain it to you first. This is the percentage of the total population. The blue is males on this side, and the pink is females. So, and it's split in 4-year increments. So from ages 0 to 4, 3% of the population is male, 2.9 is female. 5.9 from 5 to 9, 3.2% is male, 3.0% is female. And this would total up to 100% when I add up both sides percentages. Tells us where they're split up. But the important thing I want you to look at here is realize, why does this affect us in everyday life economically. Well, notably, people only from about this age to about this age work. They're the ones making money. They're supporting the young ones here who aren't working and the older ones here. Now, we don't have as many older ones because they're dying as they get older. But as long as this is the biggest chunk, we're in pretty good shape economically. Now, a lot of the problems we have with Russia, or as called when I was younger, before they put the Soviet Union, you can see something here. It's very interesting. There are a lot more females than there are males. And that causes a problem because you need the same two things. You need the same amount of females and males to continue the population. Number two, if you notice here, there are a lot more females of older age than there are females of younger age. This causes an additional problem because it's younger females that have children that continue population. And when we have older females outnumbering younger females, that means the populations that keep dwindling and dwindling. And this happened for three major reasons. Right now, Russia has a population of 145 million. They had 210 million in 1930. They've still not recovered from that. And that's for three reasons. Number one, the Stalinist purges. Joseph Stalin, when he was the um, the dictator of Russia, basically, he had another 10 million men, mostly men, killed who didn't agree with him. Usually politicians, excuse me, scientists, engineers, academics, anyone with intelligence. He also killed another 5 million people by starving Ukraine because they would not agree with him. It's not the first time Ukraine had problems with Russia. The second thing is to look at here is World War II. The United States lost 500,000 men. In Russia, they lost 20 million men, which basically 10% of their population. So they lost almost 15, 16 million men in this population. And you can see to this day, 80, 90 years later, it's still not recovered from that. And like I said, you can see where you got less younger people and older people. You got a lot of older people, which means the only ones that are working are right here. There's not many of them. Now, I was talking about the older females or younger females. If a woman is having unprotected sex between ages 20 and 24, there's an 86% chance she'll get pregnant in 3 months. That goes down as you notice. 78% chance 25 29, 63 to 30 34. And by the time a woman is 50, it's almost impossible to get pregnant. Only about 5% chance in 45 and 49. So when you look back at Russia, there's more older women and younger women. There's not enough younger women having kids. There's not enough men to have an equal distribution of males and females. And we can basically determine growth rates of a population by looking at the birth rate and the death rate. Now, here in the United States, we almost got pretty much a zero population growth. We're very slow. It means the same number of people being born as are dying. The population growth rate basically is slightly growing here, but when you combine these two polynomials together, and that's what these are, polynomials, you get this overall equation, which shows an overall slight growth. Now, what we've done here before is we're looking at the slope as we did. I took two equations here. I'm sorry, 2 points here. 0.139, 0.215, and 45. We found this a little while ago. 45 minus 9 is 36. My y2 minus y1. My x minus x1 is 15 minus 3, which is 12. 36 over 12 equals 3. So I got a positive slope here. Now I can do this over any period, and that's what I wanted to show you here. We did this for one point right here, and I've done it for all 4 different points here. I found every slope here from -4, 0 to -2, 2. That's what that line is here. And then this line from -2, 2 to point C, which is 0, 4. Then from 0, 4 to 220. And then my final slope from point A, -4, 0 to D, 20. And I'm just going to solve each one of these here. I've just subtracted each one of my distant one was letter B, C, or D from the A, was B or C. I found, and you can see I have a positive slope here in this first one. And that makes sense. Anything that's positive up and to the right. Anything that's negative is going to be down to the right. And I just do use this as a little gut check here. From point A to point B, which is this -4 to 12 to -4 to 0, 2 to 12. And I get a slope of 6. And then from -212 to 0, 4, which I've done on the second one right here, I get a slope of -4. And it is negative. It's going down to the right here. The third one, which is going from 0 to 4 to 220, it's got a very high slope. And that is 20 minus 4, which is 16, over 2 minus 0, which is 2. 16 over 2 is 8. And then when I take the final slope from point A to point D, the very first point here, the very last point here, 20 minus 0 is 20. 2 minus -4, same as 2 plus 4, which is 6. 2 over 6 is 3.333. So you can see I have various slopes going from one point to another here. And I can calculate each one of them using basically the slope formula. And by the way, that slope formula is known as M. You're going to see, we continue talking about algebra, y equals mx plus b. M is the slope. Quick refresher here. Remember, we can only add like terms. That not only in terms of variables, also the same degrees. 3x plus 5x is 8x. 4x squared minus x squared is 3x squared. I cannot add different variables and or different exponents. 3x plus 4x squared is not 7x squared. I got 2 different degrees here. This is 1, x to the 1, this is x squared right here. 12x plus 15y is not 27xy. And also, we talked about in standard form, that's going from highest to lowest formula. I've got this series of 2 equations adding up. And notice, in the end, I have to put my highest degree first. Not the highest coefficient, of number one, but the highest degree, which is 4x to the 5th. Followed by the second one, which is 6x to the 4th. And I got that from -3x to the 4th here, plus 9x to the 4th, which is 6x to the 4th. And I just add these all down through here. But notice I go from the highest efficient to the second highest, the third, fourth, fifth, and then the last one right here. Another place we use polynomials is in agriculture, actually in pest control. One of the biggest detriments to our citrus crops in the United States, California, is the cottony cushion scale. That is this big waxy bug on the left here I'm pointing to. These are ladybugs. They love eating cottony cushion scales. Cottony cushion scale really almost destroyed our orange crops in California. This is back in the 1800s. And part of the problem was with insecticides. That white covering you see in the cottony cushion scale, it, for lack of a better term, it pretty much laughs insecticides because it's made of wax, and insecticides just bounce right off of it. But what happens is these young ladybugs they introduced from Australia love eating these things, especially the ladybug larvae, which are actually voracious. And we can determine a control with polynomial functions for pest control. Right here is there's the equation of the cottony cushion scale growth when this ladybug is introduced right here. And as you can see, it starts going down as it starts going up. And they reach a critical point right here where there's slightly more ladybugs than there are cottony cushion scales. And we don't want the ladybugs to go all the way altogether. You have some cottony cushion scales, but it keeps it under control. Because if all the Connie-Cushing scales are wiped out, then the ladybugs won't have any food to eat either. So, but it really, we can use this as a predictor. Like if I know my Connie-Cushing scales at this point, how many more days do I have? Oh, right here. It's right here. At the worst, it'll be 50 days from here to here. And who knows? If I know when it starts getting to these rates, then we've almost controlled our Connie-Cushing scale. Now, real quick here, multiplying polynomials, we use the distributed properties. I got 6z squared times 7z squared plus 3z minus 2. 6 times 6z squared, 7z squared is 42z to the fourth. 6z squared times 3z is 18z cubed. 6z squared times minus 2 is minus 12z squared. And I just put all three of those up here from highest to lowest degree. And even when I'm multiplying uh, I know the trinomial, I like using distributive property and keeping it track one at a time. I'm going to use this first factor here, multiply this second trinomial. 1 times x squared, right here. Then 1 times minus 5x, and 1 times minus 6. So now I've gotten the first part done. And I'm just keeping them in order so I don't make a mistake. Then I've got my second, my x. X times x squared is x cubed. X times negative 5x squared. X times minus 6 is minus 6x. And I'm just going to add all these together, which I've done right here, but I'm going to put it in from highest to lowest degree. Here's my highest one is x cubed. I've got an x squared minus 5x squared, which is minus 4x squared. I've got minus 5x, minus 6x, minus 11x. And then I've got a minus 6, it's the only other constant. And that's it. I know I'll put it from highest to lowest degree. Another place we add these two together is very interesting, actually, and I worked quite a bit in healthcare for years, is these are the mortality rates. Mortality, you usually look at per 1,000 individuals. So this is a death rate right here, 20 people per 1,000, 40 people per 1,000, 60 people per 1,000. And this basically shows what the death rate is for diabetes per 1,000 people. That's the equation we can predict. This is the death rate for hypertension, high blood pressure. And they're often interrelated. And what we found out if we can control these together, add these up, we have a much more death rate here, hypertension and high blood pressure. That is the equation right there. And that's how we work this.